Let me.
Okay. Can you hear me now?
Now I can. Yes. Yes. Great.
Now we're already live now because we start at 9 o'clock. So we're already live. So everybody can see us now.
Good. So
No
hi,
problem.
everyone. I had some trouble logging in. Sorry for the delay.
No problem. Now I'll switch the screen to our faces. Just a moment. So we'll go like this. I'll briefly introduce you for about 1 to 2 minutes, and then we'll start the guided reading. So I'll start now. So hi, good morning, good afternoon, and good evening, everyone. This is our live stream of the way of reading. This is our 124th session now. In today's live stream, we are very honored to have Professor Tiago Torrent with us. Professor Torrent will guide us through one of his recent papers titled Representing Context in FrameNet, a multi-dimensional multi-modal approach. So Professor Tiago Torrent is a prominent cognitive linguist who specializes in natural language understanding using frame semantics and construction grammar. And he's the principal investigator of the FrameNet Brazil Computational Linguistics Lab at the Federal University of Juiz de Fora in Brazil. Now, his research focuses on developing NLU systems based on theoretical frameworks of frame semantics and construction grammar, and he has published extensively on this topic and in related area. One of his recent interests includes the application of generative AIs as tools for linguistic research. He has co-authored a Cambridge element titled Copilot for Linguists, which we read together in a live stream session under the guidance of Professor Thomas Hoffman. I believe many of you in today's live stream also participated in that session, and we have learned a lot from reading that book. We will also benefit greatly from today's guided reading session. So without further ado, please join me in welcoming Professor Torrent by clicking on the like button on the screen. So Professor Torrent, thank you very much for joining with us. And now I will give you the co-host. I set you as a co-host. Then if you share the screen and everybody could see it.
Yes.
Now I have make you the co-host. The floor is yours now.
Okay, thank you so much, Michael. I'd like to thank you very much for inviting me. It's a great pleasure to be here with you today. And thanks everyone who is watching us live. So we published this paper under a thematic issue of Frontiers in Psychology that was focusing on approaching the notion of context, right, from several perspectives. And we contributed this paper on the representation of context in FrameNet. The subtitle of this paper, A Multi-dimensional Multi-modal Approach, focuses on the two main differences that FrameNet Brazil brings to the FrameNet world in terms of representation of semantics and pragmatics of language. So I'm going to skip the abstract, if you don't mind, because pretty much it summarizes the reading that we're going to have throughout this session, just to make sure that we will be able to cover, if not everything, most of the paper during our remaining 54 minutes, right? So, Michael, if that's okay with you, I'll be reading, and when needed, I'll stop for brief comments on the sections of the paper, okay?
Okay.
Good, all right. So I'll start with the introduction. Okay, so recent advances in computational linguistics derived from the use of contextualized embeddings such as BERT and ELMO have brought contextual information to the core of NLP, raising key issues on which kinds of information are captured by and on how they are represented in those models. Context in this scenario is broadly understood as information extracted from the set of words occurring around a given word, token. The term context is also used in NLP to refer to information that can be extracted from sentences around the one being analyzed for a given task, such as natural language generation for question answering and dialogue systems, or context-aware semantic parsing. Also, identifying and modeling common sense knowledge is a key aspect of tasks involving natural language understanding, NLU, and natural language inference, NLI. There is no consensus in linguistic theories as to a definition of context. So in this introduction of the second paragraph, what we aimed to do was to make this contrast between what people in mainstream NLP, natural language processing, usually refer to as context, which, as you will see, is a much simplified version of what linguistic theory thinks about this same term, context, right? So from now on, we're going to dive a bit into what linguists have been talking about context for a while. So as didactically explained by Deborah Schifrin in this classic 1994 book, theories may see context as the common sense knowledge needed to engage in and maintain communication, the situational framing, the texts around the phenomena under analysis, or a combination of two or three of them, right? So it's either common sense knowledge, situational framing, so what's the situation where I'm engaging in communication, be it spoken, signaled, or written, right? And also, what kind of linguistic material lies around the linguistic phenomena I'm focusing on in terms of analysis, okay? Frame semantics includes all three aspects of context listed by Schifrin to some extent. As one of the semantics of understanding, that's how Chuck Fillmore defined frame semantics in the 1985 paper. Frame semantics aims to uncover the nature of the relationship between linguistic texts and the interpreter's full understanding of the text in their contexts. Notice that it's very ambitious, right? So the interpreter's full understanding of the text in their contexts. Frames are defined as the background scenes against which the meaning of some linguistic material should be construed. Such scenes are composed of participants and props, each of which is defined as a concept or frame element, FE. FEs are related in such a way that the presence of one of them brings the others into play. Frames can thus be regarded as capable of representing important elements of common sense knowledge required for properly understanding the meaning of a given piece of language. Moreover, when defining the theory, Fillmore recognized that another important type of framing was the framing of the actual communication situation, highlighting the centrality of pragmatic frames for frame semantics. So there is a paper that I co-author with Oliver Chulu and some other collaborators on pragmatic frames. It's quite interesting too if you are interested in frame semantics and pragmatics. Finally, the surrounding text is the starting point of any frame semantic analysis, since frames are instantiated either via their evocation by specific linguistic units, the lexical units, or via their invocation by comprehenders from the combination of clues found in text. Frame semantics has been computationally implemented in the form of FrameNets, first for English, and then for several other languages, including Brazilian Portuguese, by FrameNet Brazil. Because they are structured according to the principles of frame semantics, FrameNets are in theory capable of computationally representing diverse aspects of context. In this article, we discuss the extent to which FrameNets are capable of representing context, and we demonstrate that enriching the original FrameNet database structure with other dimensions of meaning representation and other communicative modes augments this capacity of representing context. To achieve this goal, we start by briefly presenting the original Berkeley FrameNet model in section 2 and the dimensions of context it captures. Next, in section 3, we present 3 new relations added to FrameNet Brazil and discuss how they add new dimensions of meaning representation to the FrameNet model. Section 4 demonstrates how the FrameNet BR model can be extended to represent contextual information captured by the analysis of other communication modes, such as video, for example. And in Section 5, 2 experiments based on the proposals presented in the previous 2 sections have their results reported on, while Section 6 presents the conclusion of this article. Okay? So moving on to the original FrameNet structure. So Berkeley FrameNet is the original implementation of frame semantics. It started as a lexicon of the English language, which was then expanded to include other types of linguistic structure, namely constructions. So the 2 papers cited here, Filmer and collaborators 2003 and Filmer and collaborators 2012, are the papers that give us the general structure of both the lexicon in the first paper and of the constructicon, the repository of grammatical constructions, in the second paper. Each lexical unit, LU, in Berkeley FrameNet is the pairing of a lemma and the frame representing the background context against which the LU definition is to be understood. So this is a very short sentence, but it has lots of information. So we should pause for a minute here. Note that the frame is not equivalent to the definition of the meaning of a lexical unit, right? When you go to FrameNet and you open the lexical unit report, you see that lexical units have definitions just like a dictionary, regular dictionary, all right? But the thing is, you actually, when you look beyond this definition, you see the frame that is evoked by this lexical item, and this frame, the scene, is the background knowledge against which you should consider that definition, okay? That's important because some people, for example, get confused when they find antonymies words under the same frame. So, for example, under the Finnish competition frame, you have both win and lose, right? And sometimes it seems like odd because they are opposing words, but actually when you read the scene, it says that competitor 1 and competitor 2 finish a competition at a given rank. So it says nothing about necessarily winning or necessarily losing, so both verbs can be under the same frame. They will be differentiated by their definition, okay? Consider, for example, the Turing frame in figure 1, evoked by LUs such as see, tour, the verb, tour the noun, visit the verb, among others. So if we go down to figure 1, here we have the Turing frame, right? So every frame in FrameNet starts with a definition where we describe the scene. A tourist experiences a specific attraction, a specific place with a unique history or other socially recognized individual character with the goal of seeing and learning about it. Then you have the core frame elements. Here we have 3 of them. It's the attraction, the place, and the tourist, right? All core frame elements must be present for the frame to be instantiated. I tend to make a joke. I'm from a very, very small town in Minas Gerais in Brazil. And I tell people that there is no instantiation of the Turing frame there. That it's a place, but it has no attraction. Therefore, there are no tourists, right? And then you have the non-core frame elements, which may appear as additional information, but they are not mandatory for the frame to be instantiated. So here we have some of them which are pretty general, such as time or manner, right? But other are more specific, such as the co-participant that joins the tourist in the activity. Then you have a set of relations that this frame bears with other frames. So for example, it's a perspective on the attraction tourism frame, the perspective of the tourist, right? And it inherits, for example, from the perception active frame. Okay, because to see some place, to visit it, it's a kind of active perception. Right, so let's come back to the text. So as I showed you, each frame comprises a definition and a set of frame elements. The definition provides a general description of the scene represented by the frame, and in most cases, it references the FEs. The FEs in turn are classified into core and non-core, the first being mandatory for the instantiation of the frame, and the latter indicating circumstantial information that may appear in sentences featuring the frame evoking LU. In the Turing frame, the core FEs are attraction, place, and tourist. As a non-core, there are some like co-participant and time. FrameNet annotation consists of syntactically and semantically analyzing a target LU. The multi-layer lexicographic annotation consists of at least 3 layers of annotation, one for the frame elements, one for the grammatical functions, and another one for the phrase types. Figure 2 provides an example of a FrameNet annotation set for the LU visit, evoking the Turing frame. Note the annotation assigns both semantic and morphosyntactic metadata to the sentential context, also referred to as context in terms of linguistic theory of the target LU. So here is an example of an annotation in figure 2. Thousands of tourists visit Copacabana Beach in Rio de Janeiro on New Year's Eve. You have thousands of tourists as a tourist, Copacabana Beach as the attraction, in Rio de Janeiro as place, on New Year's Eve as time, right? Back to the text. Fundamentally, frames are not a set of isolated units. They are associated with other frames via a set of typed relations, or in other words, frames are organized in a net-like structure. So it's a frame net. It's not a frame list, right? It is important to note that every frame-to-frame relation is sustained by relations holding between the FEs in each frame. Berkeley FrameNet defines 7 types of relations together with a meta relation, named C also, used for editorial purposes. Filmer and Baker classified those relations in 3 groups: generalization, event structure, and systematic relations. So the generalization relations are inheritance, perspective on, and using, right? Those are the 3 generalization relations. So similarly to idea of subsumption, common in ontologies and knowledge graphs, inheritance indicates that all facts that are strictly true for the semantics of the mother frame must correspond to some equally or more specific fact associated with the daughter frame. The FEs in the mother frame must be associated with those in the daughter frame, but the latter may have different names and definitions. Also, the daughter frame may have more FEs than the mother frame. Multiple inheritance is allowed. This is an important feature of FrameNet because usually multiple inheritance is not something very common in computer science. Perspective on, this relation implements the idea of profiling, taking the figure ground distinction into consideration. Different lexical items, for example, buy and sell, may refer to an event of goods transfer, but they do so from 2 different perspectives, represented by the commerce buy and the commerce sell frames. Using this relation is mostly used for cases where part of the scene in the daughter frame refers to the mother frame. Filmer and Baker explained that the daughter frame depends on the background knowledge of the mother frame, meaning that at least some of the core FEs in both of them should be related. Some background information here. Using was the first relation Berkeley FrameNet had. And it was used for everything. And then they fine-tuned the relations to more fine-grained versions, such as perspective, inheritance, subframe. And then using became this relation that covers everything that is not the rest, right? So that's why the definition is so loose. We have 2 event structure relations, subframe and precedes. So subframe defines that a given event is a subpart of a more complex event, and precedes defines that one sub-event may precede the other sub-event. Very simple. The systematic relations causative of and inchoative of demonstrate valence alternations, right? So for example, the incausative of the mother frame represents a version of the daughter frame where the agent or cause of the event represented by the frame is profiled. So we say that cause to become dry is the causative alternation of being dry. So you can say, my clothes are dry, it's the being dry frame. But the sun dried my clothes is caused to be dry. But my clothes dried is the inchoative of being dry, right? So you either profile the cause of a state or you profile the entity that has undergone the change of state. And then this paragraph just refers to the relations in the Turing frame that I already mentioned, that it inherits perception active, right? That it uses visiting. I'm going to skip it just so we have the time to cover the key aspects of the paper. So because Berkeley FrameNet combines a structured database with annotation, associating the categories in this database to linguistic data, contextual information can be represented in Berkeley FrameNet by the frames, the FEs, the relations between them, right? By the annotated sentence or by a combination of both. In a nutshell, the original Berkeley FrameNet structure can capture contextual information of the following types. First, common sense knowledge about the participants and props usually involved in a given type of event, state, or relation, as well as information on their nature and on attributes that can be assigned to them. This information is represented from the structural point of view via the frame elements and their statuses in the frame. From the annotated data perspective, it is represented by the valence descriptions extracted from the annotation. So, for example, the Turing frame represents a kind of common sense knowledge. As I told you, if a given city or town does not have attraction, it doesn't draw tourists, period. This is common sense knowledge, right? And it's represented because of the coordinate status of attraction, place, and tourist in the Turing frame. Also, common sense knowledge about the event state relations, attributes, and entities related to the main predicate in a given sentence. This information is structurally represented via frame-to-frame relations, right? So when I tell you, for example, that Turing is a type of perception active, I'm giving you common sense knowledge about Turing, right? It can also be represented in full text annotation when all lexical units are treated as targets and their dependents are annotated, because then you build the semantic representation of a text that involves lots of common sense knowledge associated as metadata to that text in terms of the frames that are evoked. Although those types of contextual information are highly relevant, the Berkeley FrameNet structure is not capable of representing other important aspects of context already recognized as central in frame semantics theory. Regarding the contextual information anchored in the text surrounding the lexical unit under analysis, or the cotext, the BFN model can only partially capture them via annotation. Returning to the example in figure 2, note that the attraction FU was assigned to the noun phrase Copacabana Beach, here, right? Hence, in this piece of annotation, we could associate the head of the NP, beach, with the concept of attraction. This association represents a piece of common sense knowledge about tourism, namely that natural features such as beaches, mountains, and lakes have the potential to become tourist attractions. However, the current Berkeley FrameNet structure has no means of storing the generalization expressed in the previous sentence. To properly represent this and other types of contextual information in FrameNet, we propose adding other dimensions of meaning to the current frame structure. Such proposal is detailed next. So in section 3, I will be guiding you through new relations and new data structure that we added to FrameNet Brazil, right? And basically, those three relations, those new relations are the frame element to frame, the metonymy, and the ternary qualia relations, because we believe they can enhance the representation of context. So moving to 3.1, the frame element to frame relation, this relation models the fact that a given frame element in a frame may reference another frame in a FrameNet, right? So one frame element mapped to a whole other frame. Such mapping does not necessarily apply to the definition of a semantic type to the FE. Its purpose is to extend the conceptual interpretation of FEs so that besides representing the instantiation of microthematic functions in an annotation set, they may also represent common sense knowledge. Let us return to the example of the Turing frame in figure 1. This frame features three core FEs, tourist, attraction, and place. And as the discussion of the annotation set in figure 2 reveals, it is common that a part of the sentence instantiation in FE contains a lexical item that may evoke another frame. In the case of sentence in figure 2, this is what happens with the tourist FE, which is instantiated by the noun phrase thousands of tourists. the noun tourist in this noun phrase evokes the people by leisure activity frame. So one alternative for representing those kinds of connections between frames in the database could be proposing a using relation between people by leisure activity and Turing, because to understand people by leisure activity, you could have the background of Turing. Nonetheless, such a solution would be not capable of identifying that the part of the letter that refers to the first is the tourist FE. To properly represent which concept in the system of concepts, the frame, is linked to another frame, FrameNet Brazil created the FE to frame relation. In the Turing frame, this relation maps not only the tourist FE to the people by leisure activity frame, but also the place FE to the locale frame and the attraction FE to the natural features, buildings, and locale by use frames, as shown in figure 3, right? So I'm going to move to the figure and then explain it to you, and then return to the segment of the text that is relevant after the explanation. So on top, we have the Turing frame. A tourist experiences a specific attraction, a specific place, right? We have the 3 core frame elements mentioned here in the definition. And then we can say that the tourist has a frame element to frame relation with the people by leisure activity frame down here. And this frame is defined as a person is considered in regards to some leisure activity in which she is engaged, and the LUs are tourist, traveler, visitor, right? The same holds for place. It's the political locales frame. This frame covers words that define locations politically or administratively. And the attraction FE is linked to 3 other frames because there are different kinds of attractions. Some of them are natural features. Natural geographic features including land, ice forms, and bodies of water, or buildings, permanent fixed structures forming an enclosure and providing protection from the elements, or locale by use, geographic locales as defined by their use. So things such as beaches, caves, rivers, museums, pubs, saunas, parks, sanctuaries, they are all possible attractions, right? And that's how we link. There are some policies that we use to define which are the frames linked to the frame element relation, right? And those policies are summarized in those steps that are presented here. So first, for each frame, we analyze the type of concept it models. Is it an entity, right? Is this entity a human being? Is it a place, for example? Only frames indicating events, states, attributes, and relations are eligible to the frame element to frame relations. Because if it was entity, imagine people. There is one frame element person, but this frame element is the people frame. So it would be a circle, right? If the frame is an instance of the 4 types mentioned, proceed to the next step. If not, restart the process. For each core FE in a event, state, attribute, or relation frame, use information from the definition or semantic type to determine the type of concept it refers to. For each concept type, people, place, event, search the most top-level frame representing it in FrameNet. Analyze the inheritance chain of the top-level frame chosen, checking both the definitions of the frames in the chain and the LUs evoking them to choose the frame that represents the correct degree of granularity, right? So why did we choose people by leisure activity to represent the tourist? Because it's the first specific frame under people that only segments tourists, because the other would be people by vocation that has LUs such as architect, which is not a prototypical tourist, right? In this scenario. And then you create the frame element to frame relation, right? So the following paragraph just describes exactly what I told you about the tourist by leisure activity. So I'm just going to give you the figures here. The application of the eligibility criteria and the maximize informativeness principle to the FrameNet Brazil database result in the proposition of 3,582 instances of the frame element to frame relation. Out of the 1,306 frames in the FrameNet Brazil database, 1,198 or 91.7% of them have at least one instance of this relation. So it's a lot, of coverage for this relation. The average of frame element to frame relations per frame is 2.98 relations per frame. A total of 40 out of the 188 frames, 37%, that do not have any frame element to frame relation represent entities. So it would be the circularity that we avoid. The remaining 63% are distributed between non-lexical frames, so they are just there for organization, and other very high-level frames representing abstract relations or image schemata. This is to say that virtually every frame in the FrameNet Brazil database representing an event, state, attribute, or relation has at least one core frame element linked to at least one other frame in the database. Frame element to frame relations represent a sensible increase in the granularity of semantic representation provided by FrameNet Brazil. For the sake of comparison, the FrameNet Brazil database features 1,846 frame-to-frame relations of the types that we saw in section 2. Among those, 586 are using relations. If we consider all relation types, frame element to frame relations almost double the number of relations in the database. But if we consider that they are actually a specification of the using relation, right, as we saw, they increase by 7 times the number of relations. So it's a big growth in granularity. The frame element to frame relation captures important aspects of the semantics of FEs, adding a new dimension of representation of contextual information, especially common sense knowledge, to the FrameNet model. However, it's still not capable of modeling another pervasive phenomenon in language, that of metonymy. So, the metonymic substitution of frame elements. There is some consensus among researchers that both metaphor and metonymy are meaning mappings that can be differentiated by the nature of the source and target domains involved. While metaphor is a cross-domain or inter-domain mapping, meaning that at least 2 different domains are involved, metonymy is considered an intra-domain mapping. That is, it takes place within a single domain. The translation of such a distinction into the FrameNet domain results in the fact that metaphoric mappings are to be accounted for via frame-to-frame relations. One frame projects into another, right? While metonymic ones should be modeled as frame internal relations between frame elements. In the case of metaphor, the latest version of Berkeley FrameNet book includes guidelines on how metaphor should be addressed. Although no empirical validation of such proposal has been reported yet, Berkeley FrameNet already proposes a methodology for accounting for metaphoric mappings in the resource. In the case of metonymy, there are no theoretical methodological proposals by the Berkeley FrameNet team. Gamonal, a member of the FrameNet Brazil team, on the other hand, proposes a methodology for accounting for metonymic mappings in the FrameNet Brazil database via a relation between FEs, as it will be demonstrated next. To exemplify the metonymic mapping, let us consider the sentence in 1 taken from the FrameNet Brazil corpus. So, São Paulo offers bars, restaurants, street food, cafeterias, and dumpling stores for almost all tastes. So, in 1, São Paulo is a metonymically named entity. According to Lakoff, metonymies occur when a concept A and concept B, which is closely associated to A, are both contained in the conceptual structure, and B is easier to understand, recognize, or remember. Hence, referencing A via B is more immediately useful for the given purpose in the given context. In the example, we can interpret that there is a set of social organizations running business that offer food services to people. São Paulo is a political locale where such organizations are located. Hence, a sentence like 1, where the noun phrase São Paulo is the subject of the verb oferecer, offer, invites the inference that the social organizations operating in the city are being referenced. São Paulo stands out in relation to the social organizations because they are too many, too varied, and not necessarily well known to be useful for the purpose in this context. Important information, this sentence comes from a tourist guide, right? Thus, we assume that the political locale stands for the social organizations in the sentence. As presented in section 2, FrameNet analysis revolves around lexical units. A sentence like 1 could be annotated for the following LUs: offer, evoking the offer frame, bar or pub, restaurant, food truck, cafeteria, and dumpling store evoking the food services frame, and taste evoking the sensation frame. Note, however, that São Paulo would not be considered an LU evoking the political locale frame because FrameNet annotation does not take proper nouns as targets. This is a foundational methodology in FrameNet. Because FrameNet, therefore, the only means to extract contextual information about the named entity São Paulo in 1 is the linguistic annotation of offering in 2, right? So São Paulo is the offerer, okay? Metonymic substitutions such as the one exemplified in 2 are very common, and to properly represent them in FrameNet, a new relation between FEs was proposed. The metonymic mapping of FEs requires 2 steps. The first is to model via the frame element to frame relation that we just saw that the offerer FE in the offering frame can be defined by the organization frame, right? The offerer is an organization. Through this mapping, we link a frame modeling an event to another one describing an entity. Next, we go to the entity frame, right? And we connect the organization frame element with the place frame element. And then we show that the non-core frame element place can be a metonymy for the core frame element organization, and we demonstrate that in figure 4. Right? So here's the offering frame. An offer indicates that they're willing to give a theme to a petition recipient, and then it's mapped to the organization frames, which has core frame elements, the member and the organization, and peripheral, purpose and place. And then we connect place with organization via metonymy. Okay? Good. Once again, metonymy adds a lot of information. It adds a representation of a given aspect of context, of common sense knowledge that is very fundamental. But it does not solve the main granularity problem in FrameNet, which is frames subsume sometimes hundreds of lexical units, right? And a given relation between 2 frames does not mean that for every lexical unit in 1, you find a relation of the same type with a lexical unit at another. Just so you have an idea, there is a using relation connecting the ingestion frame. An ingester eats or drinks something with the food and drink frame, right? LUs such as eat and drink evoke ingestion. LUs such as pizza and beer evoke food and drinks. But you can only eat pizza and drink beer. You cannot drink pizza and eat beer, right? So there is something missing. And this thing missing is some sort of relation connecting LUs, not frames, right? So the next level of granularity is to bring the relational structure of FrameNet to the level of words, to the level of lexical units, okay? And that's what we did with the ternary qualia relations. So deriving a computational representation of context from linguistic material, for example, lexical items in a sentence, involves not only representing the meaning of such linguistic material, whatever definition of meaning is being assumed here, but also associating what is linguistically expressed with common sense knowledge. In general, computational implementations make use of ontologies to represent common sense knowledge. In the field of information science, ontologies are defined as a formalized, explicit specification of the terms in a domain and of the relations between them, given some shared conceptualization. In such a definition, formalized means machine readable. Explicit specification refers to concepts, properties, relations, functions, and restrictions, and axioms that are explicitly defined. Shared indicates that the knowledge is grounded on common sense. Conceptualization refers to some abstract model of a real-world phenomenon, right? And then the use of ontologies for representing the semantics of natural language is not free of difficulties. Huang and collaborators propose an ample discussion of the interface between lexica and ontologies. Meaning associated with words may be, in many cases, characterized as an ontological concept. Also, relations between meanings may be transposed to some extent to relations between concepts in an ontology. However, the kind of knowledge that lexica and ontologies try to capture are different in nature, although the extent of such a difference is not easily measurable. Such a distinction is even more difficult to delimit in a FrameNet-like lexicon. In principle, FrameNets are lexica. However, the motivation for organizing the lexicon in a network of frames is grounded on cognitive and conceptual principles, since the resulting resource is meant to be an implementation of a semantics of understanding, of conceptualization. Frames are cognitively inspired and therefore relate to the idea of classes in an ontology. LUs, in turn, are disambiguated lemmas, that is, they tend to bear specific meaning, which is a requirement for concepts in an ontology. However, differently from what happens with concepts in an ontology, LUs are also characterized by their use, both in terms of frame evocation and in terms of valency structure. That is, of how FEs are instantiated around them. Crucially, the meaning associated with each LU is grounded on the context of use. Hence, LUs do not have purely intrinsic meanings, such as concepts do. The attempt to ontologize Berkeley FrameNet reveal losses and distortions of the primary goal of such a lexicon, as extensive research demonstrates. Nonetheless, if there is an intention to use a FrameNet for natural language understanding tasks, some degree of formalization is necessary. So Filmer and Baker state that to some extent it is possible to think that each LUs evoke its own frame. This is to say that each frame is in a FrameNet being invoked by several different LUs actually represents the parcel of meaning that is common to each of them, or in other words, the background knowledge needed for their understanding. Each LU in turn bears another parcel of meaning which distinguishes it from the other LUs evoking the same frame. The solution adopted by FrameNet Brazil for creating a lexical ontology is based on an extrapolation of this reasoning. A lexical ontology seeks to explore the commonalities shared by lexica and ontologies at the same time that it creates mechanisms for reducing the difference between them. According to Lenti, ontologies are formal tools that may represent lexical knowledge, provided that lexical meanings can be treated as entities classified in terms of the types the ontology offers. These relations between meanings would be derived from the relations between the ontological types. Building a lexical ontology involves challenges related to polysemy and context. In other words, the fact that words may bear more than one related meaning and their meanings depend on the context they are used in poses challenges for formalizing relations between them, right? So one of those challenges that was faced by the simple ontology, I'm going to skip this part of the simple ontology to introduce the notion of extended qualia relations, right, that we have. So extended qualia relations in the simple ontology expand the generative lexicon theory qualia relations. So generative lexicon proposes that lexical meaning is structured by 4 generative factors: formal, constitutive, telic, and agentive, and they are the qualia roles. Each one of them captures how humans understand entities and their relations in the world and aims to provide some minimal explanation for the linguistic behavior or lexical items. The 4 qualia roles are defined as formal, describes the basic category for the item and provides the information that distinguishes an entity within a larger set inside its semantic domain. The constitutive expresses a variety of relations concerning the internal constitution of an entity. The telic concerns the typical function or purpose of an entity, for example, what the entity is for, and the agentive concerns the origin of an entity, its creator, or its coming into being. The 4 qualia roles represent the different dimensions in which the meaning of a lexical item may be characterized. The multidimensionality is illustrated for the word pizza in example 3, right? So if we say the kids wanted pizza, they wanted to eat pizza, so we're focusing on the purpose, the telic relation. This pizza is too difficult. It's too difficult to make, so we're focusing on the agentive quale. There was pizza all over the living room, so we're looking at pizza as a substance, so it's the formal. This whole grain flour pizza is amazing, so we're focusing on the ingredient, then it's constitutive, right? So we just use pizza, but we reference different aspects, right? So the simple ontology formalized that with subtypes of each quail. But what we actually wanted to do is go one step forward, which is, okay, but when I say that the relation between flour and pizza is constitutive, it's constitutive in a specific way because it's an ingredient. It's not the price. The price is also constitutive of a pizza, but it's different, right? And then our idea was, what if we mediated qualia relations with frames to make them more specific? And that's what ternary qualia relations stand for, right? And then this is what this figure shows. Instead of proposing completely ad hoc specifications, we resourced to the FrameNet database to specify those relations. So here, for example, we have the constitutive relations between pizza and flour mediated by the ingredients frame. So in a ternary qualia relation, one LU corresponds to one frame element in the mediating frame, so the pizza is the product, while the other LU corresponds to the material, the other frame element. So we say that LU1 product pizza is made of LU2 material flour, mediated by the ingredients frame. The same holds for food. Pizza is an exemplar of food. You have instance and type. Pizza is meant to be eaten. You have the purpose and the tool. And pizza is created by a pizza restaurant. You have the produced food and the cook, right? The resulting database structure provides a whole new dimension for analyzing the meaning of a given lexical item in context for any given sentence. FrameNet Brazil is able not only to represent the frames directly evoked by the LUs, but also the frames invoked by the ternary qualia relations holding between the LUs, including the specification of which core FEs in the mediating frame are associated with each LU. In other words, there is more information available not only for the disambiguation of Polissimos lexical items, but also for representing context and allowing for inferences. By substituting the qualia relations in 3 by the ternary qualia relations, the specification of the various dimensions of the meaning of pizza can be represented in figure 5, right? Now, all those new dimensions can be associated with strings of characters only. But every time we define frames, we resort to the image of a scene. So the next step was, given that human communication is inherently multimodal, what if we extended the FrameNet analysis to other communicative modes such as pictures and video? And that's what section 4 is all about. So in the previous section, we proposed 3 additional relations to enhance the capacity of FrameNet Brazil to represent contextual information. All of them capture 2 of 3 dimensions of context proposed by Schifrin: common sense knowledge and information in the surrounding text. Situational context is not addressed by any of the new relations. Previous research led by FrameNet teams has shed light on the possibilities and limitations of the model to represent interaction or pragmatical frames. Both groups propose analysis where grammatical constructions would evoke frames representing situational context. Nonetheless, FrameNet still lack a consistent set of frames for representing this dimension of contextual information. FrameNet Brazil approaches the question of situational context by using semiotic modes other than verbal language as proxies for assessing how frames expressed in verbal language correlate to those triggered by pictures and videos, for example. According to Belcavello and collaborators, the hypothesis is that similarly to the way in which words in a sentence evoke frames and organize their elements in the syntactic locality accompanying them, visual elements in photos, video shots, and video sequences may also, 1, evoke frames and organize their elements on the screen, or 2, work complementarily with the frame evocation patterns of sentences associated with the images, be them captions, audio, letterings, etc. As an example of one, consider picture in figure 6. So here we have a picture, right, of Kaminari Mon in Tokyo, and you have a picture of the touring frame, right? You have an attraction at a place with tourists here. Okay? This is an instantiation of the Turing frame. So the combination of different communicative modalities are defining characteristics of human expression. Recent work in computational linguistics and computer vision has resulted in data sets, several of them listed here, models, several of them listed here, and metrics focusing on multimodal processing. Nonetheless, fine-grained analysis of the semantics yielded by the combination of visual and textual modalities are still rare. To include the possibility of analyzing other communication modes within the FrameNet methodology, FrameNet Brazil has developed Karen, a multimodal annotation tool and database management application, and implements a pipeline for pre-processing multimodal corpora that includes the steps here, right? So basically, you take a video from the web or from your computer, upload it to the web tool, it segments, it extracts all the speech from the video, all the audio, converts into a MPEG file, feeds to a speech-to-text API that generates the text with timestamps, right? That goes through human validation. It also takes the images, segments them in 30 image frames per second, extract the subtitles, use TCRECT OCR, generates a timestamp text, which is also human validated. Takes the video frames, use machine vision to create bounding box around the elements, and generates everything combined with a JSON file that is timestamped, right? And then after this pipeline, we have a JSON file that contains first the text generated from the combination of audio and subtitles with start and end timestamps for each sentence, and two, coordinates of all detected visual objects and the start end of the timestamps. And then we can make this data available for the following annotation methods. Independent text annotation, so the annotator only sees the text and annotates them for frames. Independent visual annotation, the annotator only sees the images and annotate them for frames. Or text-oriented multimodal annotation, when they annotate the text first and then complement the annotation with the video, or the other way around. They annotate the image first and then they complement with the text, right? So in figure 8, we see an example of text-oriented visual annotation. Both objects 66 and 67 were annotated for the attraction tourism frame. Object 66, the Reykjavik Cathedral, instantiates the attraction FE, while object 67, the TV host, instantiates the tourist, because it was based on sentence 4. Downtown Reykjavik is famous for street art, colored sidewalks, and for some tourist attractions. So here is the tourist attraction inside the green rectangle, and here is the tourist 67 inside the purple rectangle, right? This sentence made it possible for the text annotator to choose the attraction tourism frame for the multi-word expression atrações turísticas, tourist attractions. Consider then the situation context. When a viewer sees a shot depicted in figure 8, it is natural to recognize the cathedral shown in the previous shot. The second appearance of the cathedral, now in the background, instantiates the attraction frame element, and at the same time, in the foreground, we have the host figure, which instantiates the tourist FE. With these two FEs annotated, we can say that we have the attraction tourism frame in the image matching the attraction tourism frame evoked by the multi-word expression tourist attractions. That's just one example, right? So we have 5 minutes left, right? So if you agree, Michael, what I'm going to do is just to provide a quick summary of each of the sections, but we have covered all the theory in this paper, right?
If you are not in a hurry, you can talk as much time
I can continue. That's fine for me.
Yeah, yeah,
yeah. All right, good. I'm not. So let's slow down a bit. So in the remainder of this chapter, we present the two data sets of this paper that on April 2022, when this paper was published, they were still planned data sets. But now they are both available on Hugging Face for download. They are completed and they are freely available. The first is the frame square dataset, and the second is the framed multi-30K dataset. So the frame square dataset aims to provide the means to analyze how the frame-based semantic representation of verbal language interacts with that produced by the frame-based annotation of video sequences, or more precisely, of sequences of visual frames forming a video. The effort is aimed at detecting audio and video combination possibilities in terms of frames, as in the example shown in Figure 8. Because the annotation of video sequences in correlation with linguistic data adds a whole new dimension of meaning construction possibilities, the frame square dataset was planned as a domain-specific dataset for the tourism domain. The modeling of this domain in the FrameNet Brazil database counts with all the additional dimensions described in Section 3, frame element to frame relation, metonymy, ternary qualia. Hence, the multimodal objects selected for annotation are the episodes of a TV travel series, Pedro pelo Mundo. So it's a cable TV show. There are 4 seasons in total. There are 40 episodes, and we annotated the first season, 10 episodes with 23 minutes each, right? The plot of each episode focuses on getting in contact and exploring social, economic, and cultural aspects of a location which has experienced some kind of recent transformation. Thus, what the viewer sees is Pedro Andrade, the host, trying to connect with locals instead of merely proposing a touristic view of popular places of interest. Therefore, most of the episodes focus on a specific city, like Edinburgh, but some propose a broad view of a country, like Iran, Colombia, and the already mentioned example of Iceland. The format of the show combines stand-ups, voiceover sequences, short interviews, and video clip sequences. It offers then rich material as exemplar of complex composition of audio video for meaning making. It's not the kind of common multimodal data set where you have someone cooking, right, and a fixed camera on the table, and whatever is being said is being shown. It's not a one-to-one correspondence between text and video. For each 23-minute episode, the audio transcription combined with the subtitles according to the pipeline in Figure 7 generates approximately 200 sentences, which means 2,000 sentences for the first season. Taking the FrameNet Brazil average of 6.1 annotation sets per sentence, the annotation of the whole verbal language part of the corpus should yield, when complete, approximately 12,000 annotation sets. It's more, it's almost 14,000 now that it's complete. For the video annotation, the pilot experiment yielded an average of 2.5 annotation sets per sentence, meaning an expected total of 5,000 annotation sets. It's almost 7,000 now that it's completed. All 10 episodes were submitted to the important processing pipeline. The resulting text from both speech-to-text and OCR have been reviewed, edited, and compiled by trained annotators. Once this stage is finished, the sentences are ready for annotation. In the next step, one annotator manually annotates the sentences of one episode using the FrameNet Brazil web annotation tool and following FrameNet's guidelines for full text annotation. After this, the same annotator starts the annotation of the visual elements present in the same episode of the corpus, oriented by the already concluded text annotation, right? As previously mentioned, adopting a text-oriented annotation means that the annotator looks for the evocation of the same or correlate frames annotated in text, now in the image as shown in Figure 9. So here you have the annotation of the image, right? Of this guy playing the bagpipe, okay? Nonetheless, the annotation of both modes, audio and video, does not always generate direct correlations. In episode 6 of the corpus, when visiting Edinburgh, the host says the sentence in 5. When you think of Scotland, the first things that come to mind are men in skirts, Scottish whiskey, and bagpipe. For this sentence, the annotator chose the frame people for men. It is spoken some seconds before the viewer sees the image in 9, which is this guy. As Figure 9 shows, the annotator chose people by origin as the frame evoked by object 18, right? Here. The reason behind this choice is the fact that the man depicted in the video right after the order mentions men in skirt. So the guy is wearing a kilt and playing a bagpipe. So we know that he's a Scottish person. Therefore, the people by origin frame. These represent the typical clothing and musical instrument of Scotland, respectively. This combination of factors makes it very likely to infer that what the viewer sees is a Scottish person, a Scot. Therefore, it makes it possible for the annotator to choose the people by origin frame instead of the people frame. This kind of annotation is an example of a multimodal frame mediated ternary qualia relation, right? Figure 10 shows a schematic representation of the relations in action. So in the audio, you listen man in skirt. Man evokes the people frame, right? But skirt, saya, is the category of a subtype, which is the kilt, ternary qualia relation. And the kilt is an idiosyncrasy of a Scottish person, ternary qualia relation. So you can connect the annotation for people by origin to people via this qualia relation that we already had in the database. So you see, the good thing about making the database more fine-grained is that annotation naturally yields relations between the things. We didn't build that on purpose, right? The annotation just creates this possibility. Now, the second dataset is the framed multi-30K dataset. So despite the amount of recent work focusing on developing of multilingual image description datasets, such as the one by Elliott, the multi-30K, and the significant advances obtained by research on multimodal machine translation and cross-lingual multi-image description, we argue that the further development of computational applications aimed at improving the performance of machine translation algorithms requires a multimodal, multilingual dataset that incorporates the type of fine-grained semantics only made possible by grounding textual references to specific image regions via the establishment of textual visual frame relations. In order to develop this frame-based multimodal application, our proposed model must be able not only to attribute categories to objects in the image, but also to take advantage of the relations that are established between those entities, reflecting how they interact with the world, taking into account aspects like the background scenario evoked by that particular visual scene. Current work in the field of multimodal machine translation has been focusing on expansions of the popular dataset for sentence-based image description, Flickr 30K. This dataset consists of circa 31,000 images of everyday activities, events, and scenes, each of them independently captioned by 5 annotators who are not familiar with the specific entities and circumstances described, resulting in conceptual descriptions that focus exclusively on the information that can be obtained from the image alone. The Multi-30K dataset, a multilingual extension of Flickr 30K, extends the original dataset with German translations created by professional translations over a subset of the English descriptions, and new German captions crowdsourced independently of the original English captions. The Flickr 30K entities augments the original captions from Flickr 30K with almost 200,000 coreference chains linking mentions to the same entities in an image, and 27,000 manually annotating bounding box corresponding to the noun phrases mentioning the entities. To combine the data from both Flickr 30K entities and multi-30K datasets with the network of frames and qualia relations described in the previous sections, we start by creating 5 new Brazilian Portuguese descriptions and 5 English Portuguese translations for each of the 31,000 images and correspondent English captions in the Flickr 30K dataset. For the Brazilian Portuguese caption creation task, undergrad students from our university who are native speakers of Portuguese are presented with the image and write a caption. Following the guidelines for the translation, they are also presented with the original English description, right? The task of enriching the multimodal dataset with fine-grained semantic information provided by extensive network of relations from FrameNet Brazil is achieved by use Karen. So first, all captions are pre-processed to identify the frame evoking LUs that match the object classes in the images. And then we can do the annotation. I'm going to show you the picture because it's more didactic. So you have this image, right? Of this girl tying her shoes. And then you have bounding box 1 that is referenced to by the noun phrase a girl. And then our annotator goes there and chooses the frame people by leisure activity and chooses the frame element person for this girl. And they do the same for the hair configuration frame, the sports equipment, the body movement, the locale by use, right? So the principle is the same of annotating the video, but we do that for the static images, right? And then you get correlations because girl evokes people by age. But on the image, it was people by leisure activity. So you start adding layers and layers of information, right? So the first version of this data is already released, and you can access that. So section 5 presents experiments that we conducted to test this enriched database. So the first one is that of automatic identification of frame evoking lexical units. So we built a parser for the frame evocation process using this augmented network. And we also built a post-processing, post-editing system for a machine translation algorithm, okay? So I will walk you through the two experiments using the figures, okay? So for the parser, we built a system called DAISY. It's a disambiguation algorithm for inferring the semantics of Y. Y is just an incognite. And the reason why we say for inferring the semantics of Y and not of X is because we know the semantics. We must know the semantics of X, the word preceding, to infer the semantics of Y. So basically what we do is that we use spread activation in this algorithm. So we take a word form in a sentence, and then we access the lemma that has this word form and assign to this lemma an energy level of 1. And then we go to all the LUs that feature this lemma in the network, and every time you move, you decrease the energy, okay? But if you do that for all the words in a sentence, then you activate the network of frames in FrameNet, and then you can infer which is the most likely word given the context, right? So when we used this system, we could, for example, disambiguate words like bandeja in Portuguese. Bandeja in Portuguese can be translated by two very different words in English. It can be translated by the word tray, right? A tray where you put glasses to serve people. This is a bandeja, it's a tray. Or it can be translated as a layup, which is a move in basketball where the player drops the ball in the hoop with his hands like this, which is how you hold a tray. That's why in Brazilian Portuguese, you call a layup a tray, okay? As if your hand is the tray and the ball is the glass they're going to drop in the hoop. So when you have this word bandeja in a sentence like the player converted the bandeja, so the player converted the layup, you have other words such as convert, player, that are closer to the winning moves frame evoked by layup. Then when you have the waiter dropped the tray, right? So in this system, we were able to get the correct frame assigned to the LUs in 59.1% of the cases for Brazilian Portuguese and 55.8% of the cases in English. We checked them with manually annotated data. For the second experiment, we used DAISY to create a tool for domain adaptation in neuromachine translation. So neuromachine translation uses domain adaptation when you are focusing on the translation of a specific topic. There are several techniques. One of them is feeding the system with more training data on that specific topic. The problem is that when you do domain adaptation with training, the performance of the system decreases for general translation, right? So we devised a system called Scylla, it's inspired by the monster Scylla, you know, from the Odyssey, okay? And basically the idea for this system is represented in this figure. So what we did was, we didn't do anything with training. We just take a source language sentence. Imagine that is, o jogador converteu a bandeja. The player converted the layup. And then we take this sentence in Portuguese and feed it to a neural machine translation API. We use Google Translate, version 2, back then. The thing about neural machine translation APIs is that they don't give you one translation alternative. They give you several sentences as possibilities. So we take all of them, and then we do a search for translation equivalents for the words in the FrameNet Brazil database. And then we get the list of translation alternatives. And then we discover that for bandeja, there are two of them, tray and layup, right? But we also, oh, there are fireworks now. But we also take the sentence to Daisy to frame disambiguation. So we do that for the translation alternatives. And then we realize, the system realizes, that bandeja in this context is layup, right? And then we do translation ranking. We return to the n best translations and check if one of them has layup as an alternative. If it does, we augment the rank, right? We improve their rank, and we provide this as the translation. If it doesn't, then we remove the incorrectly translated word and substitute it with the correct translation that FrameNet generated in that domain, right? That's why it's called Scylla. Scylla was a siren, very beautiful, that sang to attract the boats, but her tail was composed of 6 dragon heads, which would bite and remove the sailors from the boat. But our Scylla is nice because it removes the wrong translation and put back a better one, right? So it's a nice Scylla, not a horrible Scylla. And then we measured our system in contrast with a baseline, which was Google Translate. And if you look at the human TER, which is actually counted by humans, we take the output of the translation, give them to 3 different professional translators and count the edits. So here, the lower the score, the better. Our system performs way better than Google Translate for the translation of the domain of Olympic sports, right? It means that it, on average, requires half the editing effort from human translators than Google Translate back then would require, okay? Now we arrive to our conclusions, okay, that I will read through so that we can summarize. In this article, we discussed the extent to which the FrameNet model is capable of representing contextual information of 3 types: sentence context, common sense knowledge, and situational framing. We started by presenting the limitations of the original Berkeley FrameNet model for representing any dimension of context different from the fragments of common sense knowledge captured by frames, their FEs, and the relations between frames. We also pointed out that such knowledge is mostly captured in Berkeley FrameNet in an unstructured fashion, and that it's mostly limited to the process of frame evocation. Next, we presented and discussed 3 new types of database structure implemented in FrameNet Brazil to both enrich the representation of common sense knowledge and provide a structured means for representing sentence code text in the database: frame element to frame, metonymy, and ternary qualia relations. Those new dimensions of meaning and context representation allow FrameNet Brazil to capture and represent information derived not only from frame evocation, but also from frame invocation processes. We also discussed how the expansion of the FrameNet model to the treatment of multimodal data can be used as a proxy for studying extra-linguistic contextual information. To discuss the potential of such an enrichment of the model, we present the plans for building 2 multimodal datasets, not plans anymore, they are done, and reported on 2 experiments relying on the multidimensional FrameNet Brazil database structure for tackling the problems of semantic role labeling and domain adaptation for languages other than English. Although the new additions to the FrameNet model presented in this article do not fully address the issues related to frame invocation and situational framing, they do represent a sensible advance in the FrameNet model for the representation of context. In future work, we plan to add new layers of contextual representation to the FrameNet model, including means for addressing those issues. So that's it. Thank you so much, Michael, for having me. Thank you so much for paying attention and bearing with us, hopefully. And I'm at your disposal for extended conversations. If you have questions, do not hesitate to email me or search for me on Twitter. My username is Torrent Thiago, so @Torrent Thiago, and my email is my first name dot my last name @ufjf.br. So it's been a pleasure.
Sure. Thank you very much. It's our pleasure to have you with us in the live stream. And as a researcher who is also working with FrameNet and frame semantics, I'm very excited to see all these useful features that you and your colleague added to the original FrameNet. And we will take some questions from the audience in the live stream studio. And 1,300 people have watched the live stream. You have received 2,600 likes. People are clicking on the like button like crazy. So while, and everyone, if you have any question to ask Professor Torrent, please submit your questions through the comment section, and I will read your question to Professor Torrent. While they are probably preparing for their questions, I will take the privilege of being a host to ask the first question.
Sure.
So my first question is related to some technical challenge that I'm facing now, because I'm also very interested in the frame element to frame relations. I annotated the entire COCA with semantic frames defined in FrameNet. So I have all the distribution informations of every frame in a sentence. So I want to know the co-occurrence or the association strings between frames. But like what you did in your paper, I only want to confine the relation within one frame. I want to know the frame, the relationship between the frame and the frame element of another frame. But sometimes some frames in a sentence, they occur outside the scope of that frame. Now, is there any way to, just technically, because this is a large corpus, I want this to happen automatically. Is there a way to just extract those frames that are only happen within the inner frame elements of the target frame, and exclude the other frames in a sentence?
Yeah, yes. If you want to extract the ones that are annotated within the sentence and for that frame, you could, for example, if you use Lome, for example, to parse the whole corpus, right? In the output file of Lome, you can identify which frame elements belong to which frame. There is a means of doing that. So in a separate project that we are doing, for identifying, for early identification of violence against women in healthcare protocols, we had parsed, of course, after anonymization in a completely secure environment, so on and so forth. We have parsed e-medical records to identify patterns of gender-based violence before the victim speaks up about the violence, right? And then the resulting JSON file from Lome, from the Carnegie Mellon frame semantic parser, allows you to specifically identify which segments of which sentence are associated with one frame but not the other. You can filter those out, right? Usually their performance for English in the exact match is of 61%. 61 is the score. usually for the exact match. So it's good. It's very far away from perfection, but for what we have for frame semantics, it's pretty much the best. So I would go with Lomi and filter out in the resulting JSON file.
Okay, I didn't
Okay.
use Lomi to for the frame annotation. Actually, I trained a large language model, Roberta to be specific. I
Right.
trained it with the FrameNet data, and then I use it to annotate. I achieved a F1 score of 0.95. It's pretty high.
Good.
Yeah.
Yes.
But
very
it does
good.
not tell me the information it wants. It just tell me
But
what
you know that
frame is
Lomi
happening in the
outputs.
sentence.
Yeah. So if you want to, yeah, when we started asking the question, because there is one thing that we called in the global FrameNet community, which is the challenge of getting the gist frame, right? So what's the gist of the sentence? What's the general frame, the most prominent frame in that sentence? And it comes from one very good example that Chuck Filmer did, which is, he says, I remember when I was a kid, I couldn't wait until the next morning to open the presents. This is the Christmas frame, but there is not a single word in this sentence that evokes the Christmas frame alone. Kid does not evoke Christmas alone. Next morning does not. Presents do not. But in combination with your contextual knowledge of Western traditions about Christmas, you know he's talking about Christmas. That, my friend, is $1 million question.
Yeah.
How do you get from people by age, kid, temporal collocation, when, possibility, couldn't, waiting, wait, the next morning, calendric unit, open, opening, present, present, into Christmas? That's, I wouldn't say it's $1 million, but a couple $1,000s questions. So it's for sure a PhD dissertation topic. You know, like exploring the connections and the different weights that you would assign to each frame to be able to infer the invoked frame is one thing that we must address in FrameNet that is not addressed so far.
I kind of thinking that if we submit this sentence to ChatGPT, I'm pretty confident that he will give us a right answer. If you ask it what it infers, ChatGPT will return with the right answer. Does this mean ChatGPT can solve the problem?
I'm not sure. As you saw with some of our experiments on copilots for linguists, ChatGPT tends to be very good with entity frames. And my guess, and we actually mentioned that in the book, is because of how large language models represent semantic relations between words with vector spaces, right? But it's an experiment that could be done maybe for the concepts that would surface a lot on training data, such as Christmas, for example. This is a good example. But I don't know if it scales. But it's a good test.
We can try it now.
Yeah,
we can try it with ChatGPT. We can try it now.
Yeah.
It's
like we could do, for example, with we could come up with a test set with several inferences of different levels of frames to see how well it performs with those different concepts.
So let me ask GPT this question. So I can, as a kid, it seems that the survey is done. The GPT survey is done today. There's nothing on the screen. As a kid, I couldn't wait
until the next morning to open the presents.
Until the next morning to open the gift. Okay. What event is this sentence inferring? Okay, the server is down today.
Oh,
I don't know why. It happened several times today because, yeah.
Yeah, it's just to create some sort of suspicious atmosphere, but I can
No,
try.
just the OpenAI has some connection problem. I cannot connect to OpenAI. This happened several times today. Maybe their servers have some problems today. Well, by the way, since I have already opened this browser, this is Professor Torrent's personal website. If you want to know more about Professor Torrent and his publications, please visit this site. And this is his X page, Twitter page. Yeah. So please visit Professor Torrent page and learn more about his interest and his publications. And this is a global FrameNet that Professor Torrent just mentioned. It's a very ambitious program, but it will contribute a lot to the FrameNet project. So let's see, is there any question from the audience? One audience commented that it is very informative. It needs some more time to process it. Yes, some part of the paper is very technical. You not only need some theoretical background, but also need some technical background to fully understand this paper. Zero, he said, I'm very interested in frame semantic theory. Okay, but he has not asked the full question yet. Many people are interested in frame semantics in China. And so judging from the numbers of participants here.
Cool. Well, yeah, I was surprised. 1,300 people is like, so cool.
We have a large population. So
yes, I know, but even considering the population, I'm now considering myself famous. I'm just, I think I never spoke.
So because you are famous, that's why so many people come to the live stream.
Oh, that's so good. Thank you so much.
Oh, so then if you have here comes his question, her question, I don't know. So he said that someone said not every word is in a frame. Well, I have been asked this question before by a student, because FrameNet does not include every word. Some of the words, like you said, terminologies, those proper nouns, they're not included. And as far as I know, many of the adverbs are not included as a
there is some coverage. So there are two reasons for this partial coverage, right? There is one, which is it's just because we still didn't have the time. But like the theory, that there's nothing blocking either in the theory or in the implementation for those words to be included. This is true for adverbs, prepositions, conjunctions, numbers. They are just not there because we didn't have the time, right?
I agree. I'm of the
reason number one. But there are some other that are not there because either we don't have a frame structure that can accommodate them, right? So for example, proper nouns. Proper nouns is one of those cases. We just don't have a means of representing that. And also very pragmatic constructions, right? Because they demonstrate, for example, surprise or things like that, right? So those are the two reasons. But the thing is, when we do this kind of augmentation of the database, we can accommodate different kinds of things. For example, when we have pragmatic frames, we can start accommodating different kinds of words, different kinds of constructions, right? Which are interesting. But eventually, they will cover everything, hopefully. But we have to overcome those two challenges. Time, so we have the time to add everything, And that's why we tried with copilots for linguists. Can we semi-automatize this process? Make it faster? We believe we can. So ChatGPT and Hugging Chat were very good in proposing new LUs. Those of you who went through the book saw that, right? So augmenting the existing frames with new LUs is something that AI is good at, and we should take advantage of that, right? But on the other hand, for some more complex cases, we would have to change the way we define frames, not throw the ones we have away because they are good for the job they do, but add new kinds of frames. Frames, for example, for speech acts, right? That have bring a challenge for annotation.
Theoretically, as a theory, frame semantics should cover all the lexical units. It's just the FrameNet project has not covered all the lexical units yet.
Yes,
I think that's why that's his question.
Yeah, to be very precise, Michael, Chuck Filmer wouldn't say that every lexical unit evokes a frame, because he wouldn't say that every construction evokes a frame. And because lexical units are lexical constructions, then he wouldn't make this compromise. He wouldn't commit to that. I wouldn't too. I think that there are constructions and there are lexical items that are only procedural. They do not have frame semantics like function or meaning, right? But most of them, yes, they would evoke a frame. Okay?
Okay. Thank you. So there's another question. He continued to ask how to distinguish any from some using frame semantics.
Very good question.
From some.
Yes. So when you have the distinctions between any and some, you are having as a background frame different notions of inclusion. Right? So you would have a being included frame in the background with different perspectives that would be modulated by the presence or absence of a negative. Right? So when you say, I don't have any money, you are taking this perspective to the extreme of the possession continuum and say, there is no money with me. But for example, if a friend asks you, so do you have some money to lend me? And then this person could say, well, I don't have some money, I have all the money you need. Then the negative, like right, brings a different perspective on the quantification. So the thing about frame semantics is that when you conceive of the scene that is in the background, you bring together everything that cognitive linguistics has to offer. You bring scales, position on a scale, for example, right? So you do have different possibilities of assessing the meaning of a word, given the background scene.
Yeah, thank you. I thank you on behalf of this audience.
Okay.
Currently there's no more question from the audience, but okay, I do have another question.
All right.
Have you compared the neural machine translation system that you mentioned in the paper? Because the paper was published 2022 before the advent of the generative AI. Have you compared that with GPT or other large language models? Because according to my experiments, the GPT outperforms the existing machine translation systems a long way. Google, DeepL, outperforms all of them.
We are in this process, but what we're doing now is that we are using the multimodal data set as well. So we are still running the experiments. We don't have any metrics ready yet, but it will be reported on soon, because the student who is conducting those experiments is to finish his PhD dissertation by July, and those figures and metrics should be there. But soon enough, we will have that. I still hadn't have the time to run all the experiments in comparison after those models such as GPT 3.5, 4, 4.0. No, not yet, but it's on the radar.
Thanks.
Okay. Good.
Okay. If there's no more question, by the way, we are 4,200 likes now.
Oh, cool. So nice. Thank you.
If there's no more question from the audience, and we'll call it a day. Thank you again, Professor Torrent. Thank you
Thank
for
you so much.
joining us with this. I hope to see you again in the future in the live streams.
Sure. Yes.
Okay. So that's the end of our live stream.
Yeah.
See you, everyone, and see you, Professor Torrent.
Thank you so much. See you. Bye-bye, everyone.